solubility. The solubility is the maximum amount of solute that can dissolve in a given solvent. So how do scientists actually determine the solubility? They do experiment, right? So what I do is actually at a given volume of solvent, I start to throw in my solute. Once I throw in, I'm going to stir. If it becomes transparent, I know I haven't reached my maximum. I can keep throwing and keep stirring. And at some point, I will find that no matter how hard I stir the solution, I will always see some precipitation at the bottom of my beakers. Then I know I reached the maximum amount of solute I can dump into the solvent to form my solution. And that amount will be the solubility of that specific substance. To visualize these things, assuming today you have a beaker, you fill in the beaker with water. Then we start to throw in your solute. For example, you throw in the sodium chloride salt. Then you will see those things go down to the bottom of the beaker. And then when you stir, these things start to disappear because the sodium chloride salt is going to become sodium plus and the Cl minus. And then they are going to mix well with your water molecules and become invisible. You can see I put this little S, indicates this is actually salt. It's white powder. If you don't stir, you will actually see them stay there for some time, but it will disappear. That's because this ionic salt is going to become sodium plus and chloride minus. Once that goes into the solution, you don't see it anymore. You can keep throwing these things in, and then after some time, you will see that if you, after stirring, you're going to have many sodium plus chloride minus inside your beaker, which is invisible, but you can still see tiny amount of the salt still at the bottom. If you keep stirring, then all the things will disappear. What you should realize is that there are two things actually happening at the same time now. One is actually your sodium chloride salt become invisible sodium plus and chloride minus. That's actually one thing. But when you have actually more and more sodium plus and chloride minus exist in your solution, it's also going to start to form the salt too. So these two will become an equilibrium process. It's a dynamic equilibrium. It means actually both directions is actually happening all the time. But in the very beginning, because when you're throwing all those solids into your water, you have maximum amount of sodium chloride. You pretty much don't have this. So because of that situation, you will actually ensure that you have maximized this process. Okay, the reaction is going to the right. But as time goes by, okay, the concentration of the sodium plus and the Cl minus is going to increase. And in the end, actually, you reach an equilibrium. That means actually the ray go to the left and the ray go to the right. They will be the same. Okay, so under that situation, we call the system reach equilibrium. At certain points, okay, no matter how you stir it, okay, you will always see some remaining salt at the bottom, right? Then that's how you determine the solubility. So with that concept in mind, another thing that you should know is actually, let's say, one very interesting phenomena called the supersaturated solution. We know what is solubility, right? And the solubility is actually temperature dependent. If today you do things at 25 degrees C, which is room temperature, and then you do the solubility test of your salt, let's say 40 grams of sodium chloride can be dissolved into your water. Imagine you do exactly the same experiment at 100 degrees C. You can actually dissolve more of the salt into the water. So now imagine that, let's say at 100 degrees C, you can dissolve 80 grams of salt. And then you turn off your salt. Let the temperature slowly goes down. And let it go back to room temperature. What you are going to observe is that at 100 degrees C is transparent solution. When it goes down to 25 degrees C, what you're going to see is still a transparent solution. And that is actually a very strange thing. right? Because you know if you do the same thing at 25 degrees C, the maximum amount of solute you can dump in is only 40 grams. Okay, but right now, since you start from 80, when you go to 25, you should see things to precipitate out. But the fact is actually you won't. The solution is actually existing at a quasi-equilibrium state. Okay, that means actually it doesn't know its temperature has changed that much. Under these conditions, we call this as a supersaturated solution because it dissolves more than it should. Okay, it's supersaturated. At this time, if you just use touch the beaker, you perturb the system a little bit, then what you're going to see suddenly is actually it starts to form this little thing. Okay, and it's the salt crystals is actually forming inside your solution. And then in the end, you see something like this. So under this situation, if you just pour out those solutions and then you measure the concentration of the salt, you actually go back to 40 grams per liter. Next thing we're going to talk about the factors that determine the solubility. The first concept you should know is so-called the like, dissolve, like. Specifically, okay, in this case, the things you want to actually use is these two functional groups a lot. One of the very important concepts for the water solution is that water forms the very famous hydrogen bond. And then if you want to form a hydrogen bond, typically you will need an atom of oxygen or nitrogen. Okay, that's why I put this NH and OH here. So those are the key atoms you should look for when you see a chemical formula. So if the molecules that actually have these two specific functional groups that tend to dissolve with each other. One quick example, H2O and CH3CH2OH. When you have this OH or NH functional group inside your chemical formula, it is an indication that it can form hydrogen bond. That means actually both of these molecules, they are hydrophilic. Hydrophilic means actually they have water. Philic means actually they hate water. So since both two molecules has this OH, right? So it means actually they are more like they are all hydrophilic molecules. They are alike. So would these two molecules dissolve with each other? The answer will be yes. Second question, would H2O and this very long archaeal chain dissolve with each other? No. Why? There are no OH or NH in this long archaeal chain, right? What is this archaeal chain? Carbon hydrogen compounds. So everybody knows the oil doesn't dissolve with water, right? What is the chemical formula of oil? It's just tons of carbon and hydrogen. So if you see a compound with a chemical formula only have carbon and hydrogen, okay, the more carbon and hydrogen you have, it's more hydrophobic. Therefore, it doesn't like hydrophilic molecule. Like water is very hydrophilic. So in the second case, okay, you know they are not going to dissolve with each other. How about the third one? Okay, does the molecule has OH? Yes, okay, so indicates that part is hydrophilic. But if you look at this molecule, does it have a lot of carbons? What does that mean? It's hydrophobic, right? That means actually it's hydrophilic on one end, hydrophobic on the other. So what's the end result? Not completely, yes, that's the concept, okay, so slightly. Okay, so some other factors we need to consider. If today you have the example I gave you, they are all liquid solution. Okay, so what if today you have solid liquid solution? So this part is getting a little bit more trickier. So but the rule of thumb is actually if the solid molecule is polar, then it will dissolve in water. So here we mentioned about a keyword called the polar solid. So this one will be a little bit more challenging and require a little bit more chemical knowledge. For example, this guy, what's this? Sugar. Assuming you know the structure, it's very easy to answer the questions. Okay, so that is the structure. Would this substance dissolve in water? Yes, very easy, right? We have so many OH. It's forming the hydrogen. So solubility of this one in water is very, very good. How about I2? Is this a polar or non-polar molecule? Non-polar, right? So this is actually non-polar, but the water is actually a very polar molecule. Therefore, they are not alike. They don't dissolve with each other. But again, this actually requires you have a better knowledge about the structure of the molecule to predict whether the things is going to dissolve with each other. The next thing is factors that affect your solubility. So let's first talk about the temperature. When you talk about the effect of temperature, you want to be careful because it depending on the type of solute you have. If your solute is liquid or solid, when you increase the temperature, typically the solubility increase. So that's actually a general rules that you should remember. Of course, sometimes you will see some substance that actually have the opposite effect. But don't worry, you won't be tested for those special cases. However, if today what you have is a gas solute, then if you increase the temperature, the solubility is going to decrease. And I guess this is actually, you see these things all the time, right? Okay. If you have a Coke, okay, at room temperature, you can enjoy the fizzy feelings very well, right? But if you put your Coke, you heat your Coke, okay, you microwave your Coke for a minute, drink it again, you feel like the fizzy feeling is gone, right? Why? Because all the bubbles, all the CO2 originally dissolved in your Coke, they just go out. The solubility actually decreases. So it's very different behavior between the solid and the liquid solute. All right, so the very last things that we want to go through is the effect of pressures. So the pressure doesn't have too much effect for the solid solute, but it has profound effects if your solute is gas. So the idea is actually very easy. Okay, so think about you're actually making the soda. Okay, you're going to pump your CO2 into water. So you can think about if I exert a higher pressure of CO2, there'll be more CO2 molecules goes into my water, right? Based on that concept, scientists find out that the amount of gas that's going to dissolve inside your water can be described by the so-called the Henry's law. C is the solubility of your gas. K is the Henry's constant. And P is the pressure that you provide on the solution. So it follows a linear relationship. So from your textbook, you can actually find all the Henry's constant for all different gases. If you're going to be tested for this concept, this is actually going to be provided. And then the question you're going to encounter is like this. What pressure of CO2 is required to keep the concentration of CO2 in a bottle of root beer at 0.13 m? Apparently, this is talking about the effect of pressure on the solubility in aqueous solution. You should definitely go to the Henry's law equation, which is C equals to K times P. So right now, you know the concentration is actually 0.13. K, you know it's CO2, right? So I'm going to go back to this table, check out the K. K is 2.3 times 10 to the negative 2. And then you want to find out what the pressure you need to actually exert. Key is what? The key is can you actually recognize these questions is testing your understanding about the effect of pressure on the solubility of gas in your water solution. If you know that, then you know that's actually only equation you can use, which is actually Henry's law equation. And then all you need to do is actually plug in the information you got from the questions and solve for the unknowns.